Today on Macaulay Math, we're solving systems of equations. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150 Pre-Calculus, Lesson 34 on Systems of Equations. Our goals for today. We're going to solve systems of linear equations in two variables, both algebraically and graphically. We're going to solve systems of nonlinear equations in two variables, both algebraically and graphically. And we're going to solve application problems involving systems of equations. Anytime you are required to solve for two or more variables, you will need a system of equations. Solving for two variables requires two equations. Solving for three variables requires three equations, and so on. There are numerous techniques for solving systems of equations, and we will only be addressing a few. Let's get started. Okay, let's start the same way we have been lately with the definition. The graphical solution to a system of linear equations. The solution to a system of linear equation is the point which we will denote as an ordered pair where the two lines intersect. So a couple of notes that go along with that. Parallel lines do not intersect, and thus a system of parallel lines will have no solution. Two of the same lines will have an infinite points of intersection, and thus the system would have a solution of infinite points. Now, these are special cases, and they don't happen all too often. In most instances, you'll have a system of linear equations that look kind of like this. Now, this system has its equations expressed in y equals mx plus b form. And you can see that I have drawn in on this simple graph these two lines and just the graphical solution. So y equals a half x minus 1. It has a slope of a half, a y-intercept of 1, so the slope of a half, up 1, right 1, 2. And then the second equation that I have has a slope of negative 1 and a y-intercept of 2. So I start at 2, it's down 1, right 1, down 1, right 1. And we can clearly see that this point right here is that point of solution. So the graphical solution to this is just going to be the point 2, 0. Now for linear equations, Desmos will actually give you that point. So if I pull up a Desmos and I type in f of x is equal to 1/2 x minus 1 and g of x is equal to negative x plus 2, and we click right there on that point, we see that 2, 0 is the solution. Now this is the graphical solution for this system of equations, but what happens if we need to do it algebraically? So solving a system of linear equations in two variables algebraically, we have two main methods to do that. And the first one is known as substitution, and it's easiestly used when you have both of the equations in y equals mx plus b form, or at least one of those two in y equals mx plus b form. But if both of them are set in y equals mx plus b form, set the equations equal to each other, solve for x, and then substitute the x that you found in part b in either of the two original equations, and then you'll solve for y. Now, the linear combination method, which is often called row reduction, is best used for a system in the form of ax plus by equal to c form. And so what we'll do with this one is we will multiply the equations by a scalar so that one of the variables in the equation has a factor of -1 difference. And you can either do that with the x's or with the y's. And so what we're trying to get is one of these two coefficients in both the first function and the second function be off by just a factor of -1. And what will happen if you get that, when you combine the two equations by adding, one of the two variables will cancel out and you can solve for the remaining variable. And then whatever variable we solve for, we'll use that result and plug in to solve for for the remaining variable. Just some special cases that go along with that. If the equations are the same, or you can get it down to be 0 equal to 0, then the equations are the same line and there are infinite solutions. Now, if you cancel most everything out, but you get an untrue statement, and what I mean by an untrue statement is something like 3 is equal to 0. That is not a true statement. So if you get something that's untrue, the linear equations are parallel and there is no solution. You can always check that in Desmos and you'll be able to see very quickly, even if they don't look exactly like similar equations. Well, that's all the new information, so let's talk about some examples. So first, let's solve this system of linear equations by substitution. Now this, even though I said substitution was best used when you have both equations set equal to y, and that's true, but if one of the equations has already been solved for y, what you can do is you can take this expression here and plug it back in for that y equation. And what that will do for us is that's going to allow us to have an equation that has only the one variable in it, which we can then solve. So if I plug this expression in for y, I will have this 3x here plus 2 times. Now I am taking this y and I'm replacing it with this entire expression. So I have 3x plus 1. That'll still be equal to 20. Now I'm going to distribute. And that will give me 3x plus 6x plus 2 is equal to 20. We'll simplify a little bit here. And we'll say 9x plus 2 is equal to 20. We'll subtract 2. That'll give me 9x equal to 18. We'll divide by 9. That'll give me x equaling to 2. Now, this is my x coordinate for this particular problem. And I could plug it back into either equation, but we want to be as efficient as we possibly can. So this equation on top is going to be a little bit easier to use than this equation on the bottom because it's already solved for y. That is the coordinate that I still need to find. So we'll go y is equal to 3 times the 2 plus the 1, and we'll get our y coordinate to be 3 times 2 is 6. 6 plus 1 is 7. My final answer for this is going to be the ordered pair 2, 7. Put a box around that one and say we're done. Next example, solve the following system of linear equations by elimination. Now when I look at this equation, I am going to want to multiply both of these equations so that I can get a factor of -1 in either the x's or the y's. Now when I look at this, I don't think there's necessarily an quote-unquote easier variable to solve for, but I'm going to make it so I can cancel out the y's because I think that I can keep the numbers smaller by canceling out y's first. And to get that factor of -1, I need a least common multiple between 2 and 3. And the least common multiple between 2 and 3 is going to be 6. So I'm going to multiply this top equation by 3 and this bottom equation by 2. And that's what I mean by multiply the equations by a scalar so that one of the variables in each of the equation has a factor of -1. All right. Finding the least common multiple of the y's. You could have found the least common multiple of the x's. I just thought it would be easier to do that. So when I do that, I also need to distribute. And that will give me 3 times 3 is 9x. 3 times 2y will be 6y. And then 3 times 10 will be 30. 2 times 4 will be 8x. 2 times -3y will be -6y, and then 2 times 19 will be 38. So when I add these together, I get 17. And then here's the whole purpose. I get one of the variables to cancel out. Positive 6y and negative 6y. Those cancel. Need an X there. And then 30 and 38 will be 68. And now I'm going to divide by 17. And I get x is equal to. So 68 divided by 17. Well, if I go to Desmos, 68 divided by 17 is 4. So x is equal to 4. So now I have to plug x equals 4 into one of the original equations. And that'll give me 3 times 4 plus 2y is equal to 10. And so I'll have 12 plus 2y is equal to 10. And then I will subtract 12. That'll give me 2y equals to negative 2. We'll divide by 2. That'll give me y equals to negative 1. And so my final answer will be 4, negative 1. All right. And the way that you can check that is to go back into Desmos and plug these two equations in by themselves. So let's go do that real quick. And if I just go 3x plus 2y equals to 10, and then 4x minus 3y equals to 19, and hit that intersect, I get 4, negative 1. All right, next example. Application problem. Mr. McCulley goes to a flea market. On Saturday, he sells 5 wild widgets and 7 mild widgets for a total of $49. Then, on Sunday, he sold 6 wild widgets and 9 mild widgets for $58.50. Write a system of linear equations that can be used to solve for the cost of a single wild widget and a single mild widget, then solve the system. So the first thing we need to do if we're setting up a system of equations is we need to determine what the variables are. And the variables are what the question is asking you to find. We need to solve for the cost of a single wild and a single mild widget. Those two things are our variables. So first, I am going to say that W is the price of a wild widget, and M is the price of a mild widget. And so if I read through, the first one says if I sell 5 wild widgets and 7 mild widgets, that has a cost of $49. Now let's just say, as a for instance, that the cost of a wild widget was $5. If I sold one, it'd be $5. If I sold 2, it would be $10. If I sold 100, it would be $500. We do that through multiplication. So if I know how many I sold and I know the price, I can get the total revenue. So my first equation that I'm going to have here is I'm going to have 5 times the price of a wild widget plus 7 times the price of a mild widget, and that's going to equal $49. All right. And then my second equation, I sold 6 wild widgets and 9 mild widgets for $58.50. 6 wild plus 9 mild for $58.50. So the question asks us to write a system of linear equations that can be used to solve for a single wild widget and a single mild widget. Well, there's part A. but it doesn't tell me how to solve it. So let's just use Desmos to solve it for us. And so the equation that I come up with would be 7x plus 5y is equal to 49. And then 6x plus 9y is equal to 58.5. And we can click right here. And it's okay that we have decimals because remember, these are prices. So this is dollars amount. So decimals is definitely going to be okay. But whatever the X value was, that's going to be $4.50, and the Y value would be $3.50. So if I go back to this one, I can say that wild widgets cost $4.50 and mild widgets cost $3.50. Put a box around that. And we're finished. All right, last example. It says use an algebraic solution to solve a system of nonlinear equations in two variables. So let's just talk about these two equations real quick. This is a system of equations. The first one is a linear equation. The second one is a quadratic, so it's a parabola. So I have this linear equation that goes down, and I have a parabola that opens up. And the way I think of this is that there's a possibility that I could have two solutions here. So just to visualize, let's go over to Desmos and type these equations in. I have y equals negative 2x plus 2. And then I have y equals x squared minus 6. And so if I look at this, clearly I have 2 points of intersection. So the solution will be both of those 2 points. Now, yes, I can click on them, but the question asks us to do it algebraically, so we're going to want to do that. Now, I also notice that both of these equations have been solved for y. I can do a substitution, and I can set these equations equal to each other. And so I will get x squared minus 6 is equal to negative 2x plus 2. And so what I want to do here is I want to, since it's a quadratic, I'm going to set it equal to 0. I'm going to get it in ax squared plus bx plus c form. So I am going to add 2x and I'm going to subtract 2 from both sides. That will give me x squared plus 2x and then minus 8 equals to 0. Now, because the leading coefficient is 1, I'm going to at least try and factor this. And it turns out I'm going to at least try to factor this. And if it doesn't factor, then I would go to the quadratic formula. But as it turns out, this thing does factor. I need 2 factors of negative 8 that add up to positive 2. And that's pretty easy. I get x plus 4 and then x minus 2 equals to 0. And I'll just solve for x. That'll give me x equals negative 4 and positive 2. But again, I have a point of intersection and I have a point of intersection right there. So the solution to the system of equations are ordered pairs, just like in every other question that we've done so far. So I'm going to plug them both into the linear equation. We could do it into either and they'll still come out the same. And that would be okay. But I'll go y equal to negative 2 times negative 4 plus 2, and then I'll go y equals -2 times 2 plus 2. And so I'll have positive 8 and 2 will give me 10. And then I'll have -2 times 2 is -4, plus 2 would be -2. And so my final answers here will be the ordered pair -4, -10, and 2, -2. And if we go back to Desmos, 2, -2, and then the other one was -4, 10. So we are correct. Put a box around that. And that is all I got for today, folks. So, Star Wars fun fact of the day. In episode 4, Luke tells the prison guard that Chewbacca is a prisoner transfer from cell block 1138. This is an Easter egg from George Lucas's first movie, THX 1138. And it's kind of a weird B+ movie. Probably can't see it anywhere, but that's okay. It's still fun. Star Wars is awesome. That's all I got for today, folks. Have a great day. Goodbye.